Hello, sleepy genius. Another day has passed, and here you are, seeking rest beneath a sky you cannot fully see. The weight of the world can be set down now. Let your breathing slow, your shoulders drop, and your mind drift upward, toward something vast and patient. Tonight, we turn our gaze to the galaxy that holds us, the Milky Way, a river of light older than memory. From zombie stars that survive their own explosions to storms where diamonds fall like rain, the Milky Way hides wonders that break logic and bend reality. This isn't just our home, it's a living cosmic enigma, reshaping itself, swallowing entire galaxies, and unveiling secrets that rewrite everything we thought we understood about the universe. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please share your thoughts below. Now, let's begin. At the center of the Milky Way, a supermassive black hole sleeps, but sometimes it wakes with terrifying power. Imagine standing at the edge of a vast cosmic ocean, watching a giant stir beneath the surface, sending ripples of light and energy across thousands of years of space. Sagittarius A*, the black hole at our galaxy's core, weighs 1,000,000 times more than our Sun. Scientists using the Chandra X-ray Observatory detected sudden flares from this region in 2013. Eruptions so intense they illuminated gas clouds located 26,000 light-years away. These outbursts occur irregularly, perhaps once every few hundred years, like a sleeping dragon exhaling fire in its dreams. To think that the very center of our home is governed by something so powerful, yet so unpredictable, reminds us how fragile our sense of cosmic order truly is. Some stars die in the most spectacular explosions imaginable, yet they survive the blast entirely intact. Picture a star that has already burned through its fuel, collapsed into a dense white dwarf, and then begins feeding on a companion star beside it. In a 2014 study published in Nature, astronomers identified several type IX supernovas, explosions caused by these white dwarfs that should have been obliterated. Instead, the dead star remains, sitting quietly in the aftermath, continuing to orbit as if nothing happened. Researchers at the Harvard-Smithsonian Center for Astrophysics called these zombie stars, celestial objects that experience death but refuse to accept it. This reminds us that even in the cosmos, the rules we create are only approximations of a reality far stranger than we imagine. Floating through the Milky Way is a cloud so vast and so peculiar that if you could smell it, you would detect rum and synthetic raspberry. Consider drifting through Sagittarius B2, a molecular cloud located near the galactic center, roughly 390 light-years across. Scientists analyzing its composition in 2009 discovered ethyl formate, the chemical compound responsible for the flavor of raspberries and the smell of rum. This cloud contains an estimated 10 billion liters of alcohol, enough to fill every ocean on Earth trillions of times over. The discovery was made using the IRAM telescope in Spain, revealing that space is not sterile and empty, but filled with organic molecules. In a sense, the galaxy itself is brewing something ancient, a cosmic distillery operating for millions of years. Deep within certain giant stars, carbon atoms are crushed under such immense pressure that they crystallize into diamonds and fall like rain. Imagine standing beneath a sky where gemstones drift downward through layers of superheated gas, each one formed in conditions no laboratory on Earth could replicate. Research published in 2010 by astronomers at the University of Manchester suggested that white dwarfs, The remnants of stars, like our Sun, can develop diamond cores as they cool over billions of years. Some of these stars may contain diamonds the size of Earth itself, slowly solidifying in the cosmic cold. To think that the universe creates beauty even in death, forging treasure from the ashes of collapsed stars, is a reminder that transformation never truly ends. The Milky Way is not a peaceful neighbor but a cosmic predator, consuming smaller galaxies with relentless hunger. Picture streams of stars being pulled apart like threads of silk, stretched across the void as they merge into our galaxy's mass. Observations from the Sloan Digital Sky survey revealed that our galaxy is actively devouring the Sagittarius dwarf elliptical galaxy, tearing it apart over millions of years. Scientists estimate that the Milky Way has absorbed dozens of smaller galaxies throughout its lifetime, each one adding to its spiral arms and dense halo. In 2018, data from the Gaia spacecraft confirmed remnants of ancient collisions still visible in our galaxy's structure. This reminds us that survival in the cosmos often means becoming something larger, absorbing what was once separate into a new, more complex whole. Certain stars move so fast they are flung out of the Milky Way entirely, never to return. Imagine a star accelerating to 4 million kilometers per hour, propelled by gravitational forces so extreme they act like a cosmic slingshot. These hypervelocity stars were first discovered in 2005 by astronomers at the Harvard-Smithsonian Center for Astrophysics, using data from the MMT Observatory in Arizona. The mechanism behind their speed involves close encounters with Sagittarius A*, the supermassive black hole at the galactic center. When a binary star system passes too close, one star is captured while the other is ejected at incredible velocity. Researchers have identified over 20 such stars, some of which will escape the galaxy's gravity entirely within a few million years. To think that even stars can be exiled, cast into the intergalactic void, is humbling. The center of the Milky Way does not just contain alcohol, it smells like a tropical cocktail mixed in the void. Consider that the same molecular cloud, Sagittarius B2, releases ethyl formate into space, giving the region a scent profile resembling rum and ripe raspberries. This was confirmed in 2009 by researchers using the IROM radio telescope, analyzing the spectral signatures of organic compounds. The discovery suggests that complex chemistry occurs naturally in interstellar space, producing molecules that on Earth are associated with flavor and fragrance. In a sense, the universe does not merely exist, it has character, texture, and even aroma, woven into its deepest structures. Millions of planets drift through the Milky Way without a star to orbit, traveling alone in absolute darkness. Picture a world that has been ejected from its solar system, spinning silently through the void, its surface frozen and lifeless. In 2011, a study published in Nature by astronomers using gravitational microlensing estimated that there may be twice as many rogue planets as stars in our galaxy. These orphaned worlds were likely flung into space during chaotic interactions with larger planets or during the formation of their solar systems. Some may still retain warmth deep beneath their surfaces, powered by radioactive decay. This reminds us that not everything in the cosmos has a home, and some wander forever in the cold. Certain stars spin so fast they seem on the verge of tearing themselves apart. Imagine a pulsar, a neutron star no larger than a city, rotating 700 times per second, faster than any mechanical object humanity has ever built. PS RJ1748-2446A, discovered in 2006 by astronomers using the Arecibo Observatory, holds the record for the fastest known rotation. At this speed, the star's equator moves at roughly 24% the speed of light. The centrifugal force is so extreme that if it spun just slightly faster, it would rip itself apart. To think that such violence can be sustained for millions of years is a reminder that the universe operates on principles far beyond our everyday experience. Most of the Milky Way is invisible, made of something we cannot see, touch, or fully understand. Consider that roughly 85% of the galaxy's mass is dark matter, a substance that does not emit light or interact with ordinary matter except through gravity. Observations from the Planck satellite and the Dark Energy Survey have confirmed its presence by measuring how galaxies move and how light bends around massive objects. Scientists have proposed various candidates, from weakly interacting particles to primordial black holes, but no detection has been conclusive. This reminds us that we live in a galaxy we cannot fully perceive, surrounded by a presence that shapes everything yet remains beyond our grasp. The Milky Way once shone far brighter than it does today, its central black hole erupting with such force that it left scars visible across the sky. Imagine vast bubbles of energy, stretching 25,000 light-years above and below the galactic plane, glowing with the memory of ancient violence. These structures, called the Fermi bubbles, were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. Scientists believe they were created by a massive eruption from Sagittarius A*, roughly 2 to 4 million years ago, an event so powerful it reshaped the surrounding gas. The bubbles still emit gamma rays today, a faint echo of a time when our galaxy burned like a beacon. In a sense, even galaxies have histories written in light. One of the oldest stars ever discovered contains so much metal it seems impossible. Picture HD 140,283, a star located 190 light-years away. Nicknamed the Methuselah star because its estimated age is 14.5 billion years, nearly as old as the universe itself. Observations from the Hubble Space Telescope refined this measurement in 2013, sparking debates about stellar evolution. What makes this star particularly strange is its unusually high metallicity, meaning it contains more heavy elements than stars of its generation should. This suggests it may have formed in an unusual environment or absorbed material from a companion. To think that we still find stars that challenge our understanding of cosmic history reminds us how much we have yet to learn. There are stars so dense that a single teaspoon of their material would weigh as much as a mountain. Imagine holding something no larger than a sugar cube, yet it contains the mass of Mount Everest compressed into a space you could fit in your palm. Neutron stars form when massive stars collapse, crushing protons and electrons together until only neutrons remain, packed so tightly that their density exceeds anything found on Earth. Scientists at the Max Planck Institute calculated in 2017 that neutron star material reaches densities of roughly 400 trillion times that of water. A piece the size of a marble would weigh about 100 million tons. This reminds us that matter itself can be transformed beyond recognition, shaped by forces we can barely comprehend. The Milky Way contains rivers of stars flowing in coordinated streams across thousands of light-years. Picture ancient galaxies that were torn apart long ago, their stars now moving together like ghostly currents through our galaxy's halo. In 2018, astronomers using data from the Gaia spacecraft identified dozens of these stellar streams, including the Helmi stream and the Sequoia stream, remnants of dwarf galaxies consumed billions of years ago. Each stream contains thousands of stars traveling in formation, maintaining their original trajectories even after their parent galaxy was destroyed. Researchers at the University of Cambridge traced one stream back 10 billion years, revealing a collision that reshaped the early Milky Way. To think that galaxies leave behind rivers of light long after they cease to exist is humbling. Some regions of the Milky Way are so cold that atoms barely move at all. Consider the Boomerang Nebula, located 5,000 light-years away in the constellation Centaurus, where temperatures drop to 1 degree above absolute zero, making it the coldest known place in the universe. Discovered in 1980 by astronomers Keith Taylor and Mike Scarrett using the Anglo-Australian telescope, this dying star expels gas at 164 kilometers per second, causing rapid expansion that chills the material to -272 degrees Celsius. Scientists using the Atacama Large Millimeter Array in 2013 mapped its structure, finding an hourglass shape formed by powerful stellar winds. In a sense, even in the vastness of space, there are pockets where all motion nearly ceases, where the universe itself seems to hold its breath. There are stars that orbit the galactic center so quickly they complete a full revolution in just 11 years. Imagine watching a star trace a complete ellipse around the supermassive black hole, moving at speeds exceeding 8,000 kilometers per second, roughly 3% the speed of light. S2, one of the closest stars to Sagittarius A*, was monitored by astronomers at the European Southern Observatory for over 2 decades using the Very Large Telescope in Chile. In 2018, during its closest approach, the star passed within 17 light hours of the black hole, allowing scientists to test Einstein's theory of general relativity under extreme conditions. The observations confirmed that space-time itself bends near massive objects, exactly as predicted. This reminds us that the universe operates according to principles so strange they still feel like magic. The Milky Way produces roughly 7 new stars every year, each one born from collapsing clouds of gas and dust. Picture vast nurseries scattered across the spiral arms, where turbulence and gravity conspire to ignite nuclear fusion inside dense cores. The Carina Nebula, located 7,500 light-years away, is one such stellar factory containing pillars of gas where hundreds of stars are forming simultaneously. Observations from the Hubble Space Telescope in 2007 revealed newborn stars still embedded in their birth cocoons, radiating ultraviolet light that sculpts the surrounding material. Scientists estimate the Milky Way contains between 100 and 400 billion stars in total, each one a fusion reactor burning steadily for millions or billions of years. To think that creation continues endlessly, that the galaxy is always becoming something new, is a reminder that nothing in the cosmos is truly static. Certain stars pulse with such regularity they were once mistaken for alien signals. Imagine discovering a source of radio waves that repeats every 1.337 seconds with mechanical precision, so exact it seemed impossible to be natural. In 1967, astrophysicist Jocelyn Bell Burnell detected the first pulsar using a radio telescope at the University of Cambridge, initially labeling it LGM-1 for Little Green Men. Further study revealed these objects are rapidly spinning neutron stars, their magnetic fields channeling radiation into beams that sweep across space like cosmic lighthouses. The discovery earned a Nobel Prize in 1974, though controversially not for Bell Burnell herself. This reminds us that the universe can mimic intelligence, creating patterns so precise they challenge our assumptions about what is natural and what is designed. The Milky Way contains clouds of dust so thick they block all visible light, creating voids that appear completely empty. Consider the Dark Horse Nebula, a silhouette visible near the constellation Scorpius, stretching across 60 light-years of space. These dark nebulae are composed of dense molecular hydrogen mixed with carbon-based dust grains, absorbing starlight so effectively that they appear as black patches against the galactic background. Observations using infrared telescopes, which penetrate the dust, reveal that these regions are often sites of active star formation. The Pipe Nebula, another dark structure located 600 light-years away, was mapped in 2004 by astronomers at the Harvard-Smithsonian Center for Astrophysics, showing dozens of protostars hidden within. In a sense, darkness in space is not absence but potential, a womb where new light waits to be born. There are binary stars so close together they share a single atmosphere, merging into one bloated shape. Imagine two stars locked in an embrace so tight they orbit each other in hours, their outer layers blending into a common envelope of superheated gas. Contact binaries, as they are called, were first studied in detail by astronomer Zdeněk Koupal in the Ejo Wuling S. WSA Majoris, located 162 light-years away, is one such system, with two stars orbiting every 8 hours, their surfaces nearly touching. As they spiral closer over millions of years, they may eventually merge into a single, more massive star. Observations from the Kepler Space Telescope identified thousands of similar systems across the Milky Way. This reminds us that even stars are not immune to intimacy, drawn together by forces they cannot resist. Some stars explode with such violence they briefly outshine the entire Milky Way. Picture a supernova detonating in a distant spiral arm, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. Supernova 1987A, observed on February 23, 1987, was the closest supernova visible to the naked eye in nearly 400 years. Located 168,000 light-years away in the Large Magellanic Cloud. Astronomers using telescopes worldwide watched as the dying star ejected its outer layers at 30,000 kilometers per second, creating a rapidly expanding shell of gas. The explosion left behind either a neutron star or a black hole, though the remnant remains hidden behind dense debris. To think that a single star can release such power reminds us how fragile our cosmic neighborhood truly is. The Milky Way rotates so slowly that humanity has existed for less than 1,000th of a single galactic year. Consider that our Sun, located 26,000 light-years from the galactic center, takes approximately 225 million years to complete one orbit. This means the last time Earth was in its current position relative to the galaxy, dinosaurs had not yet appeared. The solar system has completed only 20 full orbits since the Sun formed 4.6 billion years ago. Measurements from the Gaia spacecraft in 2018 refined our understanding of galactic rotation, revealing that the spiral arms move at different speeds, creating traffic jams where star formation accelerates. In a sense, everything we have ever known has occurred within the briefest moment of cosmic time. There are stars made almost entirely of oxygen and carbon, remnants of nuclear fusion that burned for billions of years. Imagine a white dwarf no larger than Earth, yet containing half the mass of the Sun. Its interior crystallizing into a giant diamond as it slowly cools. BPM 37,993, located 50 light-years away in the constellation Centaurus, is one such star, estimated to contain a crystallized carbon core roughly 4,000 kilometers in diameter. Astronomers nicknamed it Lucy, after the Beatles' song Lucy in the Sky with Diamonds. Observations from the Hubble Space telescope confirmed its nature in 2004, revealing pulsations that allowed scientists to probe its internal structure. This reminds us that even in death, stars transform into something beautiful, crystallizing over trillions of years into cosmic gemstones. The Milky Way contains magnetic fields that stretch across thousands of light years, invisible threads connecting stars and nebulae. Picture currents of charged particles flowing along these fields, creating cosmic highways that guide the motion of gas and dust. Radio observations from the Jansky Very Large Array in New Mexico mapped these magnetic structures in 2019, revealing filaments that extend from the galactic center outward through the spiral arms. These fields are generated by the motion of ionized gas and the rotation of the galaxy itself, creating a web of magnetic force that influences star formation and the behavior of cosmic rays. Scientists estimate the field strength near the galactic center is roughly 1,000 times stronger than the field around Earth. In a sense, the galaxy is wired with an invisible nervous system, carrying energy and information across unimaginable distances. Some stars are so old they contain almost no elements heavier than hydrogen and helium, relics from the universe's first generation. Consider SMSS J031300.36 to 670,839.3. Discovered in 2014 by astronomers at the Australian National University, a star located 6,000 light-years away with the lowest iron content ever measured, roughly 1/1,000,000th that of the Sun. This suggests it formed shortly after the first supernova enriched the primordial gas, perhaps within the first billion years after the Big Bang. Studying such stars allows scientists to glimpse conditions in the early universe when galaxies were just beginning to form. To think that we can touch the ancient past by analyzing starlight is a reminder that light carries memory across billions of years. There are regions of the Milky Way where stars form in violent bursts, creating thousands of new suns in just a few million years. Imagine the Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, where massive stars are born in clusters so dense they illuminate the surrounding gas with intense ultraviolet radiation. This star-forming region spans 600 light-years and contains some of the most massive stars known, including R136A1, which weighs 315 times the mass of the Sun. Observations from the Hubble Space Telescope revealed that the nebula produces stars at a rate 10 times faster than similar regions in our galaxy. Scientists believe these bursts are triggered by collisions between gas clouds or by shockwaves from nearby supernova. This reminds us that creation in the cosmos is not gentle but explosive, driven by chaos as much as order. The Milky Way contains stars that have been ejected from their birthplaces and now wander between the spiral arms in exile. Picture a star born in a dense cluster, then flung outward by gravitational interactions, spending billions of years traveling through the sparse regions between the galaxy's main structures. In 2005, astronomers using the Sloan Digital Sky Survey identified populations of these interloper stars, which make up roughly 2% of the stellar halo. Their chemical compositions revealed they originated in the galactic disk, but were scattered outward through encounters with molecular clouds or passing stars. Some travel in highly elliptical orbits, diving through the disk every few 100 million years before returning to the halo. To think that even stars can become nomads, disconnected from their origins, reminds us that belonging is not guaranteed in the cosmos. Certain nebulae glow not from their own light, but from the radiation of nearby stars, creating cosmic mirrors that reflect stellar fury. Imagine the Witch Head Nebula, located 900 light-years away in the constellation Eridanus. A cloud of dust that shines blue because it scatters light from the brilliant star, right? These reflection nebulae were first studied systematically by astronomer Edwin Hubble in the 1920s, who classified them separately from emission nebulae that generate their own light through ionization. The blue color occurs because shorter wavelengths scatter more efficiently, the same phenomenon that makes Earth's sky blue. Observations from the Spitzer Space Telescope in 2009 revealed complex filaments within these clouds, shaped by magnetic fields and stellar winds. In a sense, these nebulae are cosmic canvases, painted by the light of stars they will never touch. There are stars that orbit each other so closely they will one day merge in catastrophic collisions that create explosions visible across the universe. Consider the system J0806, discovered in 2002 by astronomers at the University of Texas, where two white dwarfs orbit each other every 321 seconds, the shortest orbital period ever observed. Separated by less than 80,000 kilometers, roughly 1/5 the distance between Earth and the Moon. These stellar remnants are spiraling inward as they lose energy through gravitational waves. Einstein's theory of general relativity predicts they will merge in approximately 340,000 years, possibly triggering a type EAA supernova. The LISA gravitational wave detector, planned for launch in the 2030s, should be able to measure the ripples in space-time these systems produce. This reminds us that even the most stable-seeming orbits are temporary, destined to end in union or destruction. The Milky Way is surrounded by a halo of ancient star clusters that orbit like satellites, some containing the oldest stars in the galaxy. Picture globular clusters, spherical collections of hundreds of thousands of stars packed so densely that near their centers, stars are separated by distances smaller than our solar system. Messier 13, located 25,000 light-years away in the constellation Hercules, contains roughly 300,000 stars and was formed approximately 11.65 billion years ago. Observations from the Hubble Space Telescope revealed blue stragglers within these clusters, stars that appear younger than their neighbors, possibly formed through stellar collisions or mass transfer. The Milky Way hosts about 150 known globular clusters, each one a time capsule preserving conditions from the galaxy's early history. To think that these ancient congregations have orbited our galaxy since before Earth existed is humbling. Some stars emit beams of gamma rays so powerful they could sterilize planets from thousands of light-years away. Imagine a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, occasionally releasing bursts of high-energy radiation that flood surrounding space. SGR 1806-220, located 50,000 light-years away, produced the brightest burst ever recorded on December 27, 2004. An explosion that lasted 1/10 of a second but released more energy than the Sun produces in 150,000 years. The blast ionized Earth's upper atmosphere despite the enormous distance, causing temporary disruptions to satellite communications. Scientists estimate that if such an event occurred within 10 light-years of Earth, it could trigger a mass extinction. This reminds us that the galaxy contains weapons of unimaginable power, sleeping giants that occasionally wake to reshape their neighborhoods. The Milky Way's spiral arms are not permanent structures, but waves of density that move through the galactic disk, like ripples on a pond. Consider that the stars and gas we see concentrated in the arms are not always there, but instead pass through these regions as they orbit the galactic center. This density wave theory developed by astronomers C.C. Lin and Frank Hsu in 1964, explains why spiral patterns persist even as individual stars move at different speeds. When gas clouds enter a spiral arm, they are compressed, triggering star formation that illuminates the arm with young, bright stars. Observations from the Spitzer Space Telescope mapped the Milky Way's structure in infrared light, confirming the presence of at least 4 major spiral arms. In a sense, the galaxy's most prominent features are illusions, patterns that exist independently of the material that defines them. There are clouds in the Milky Way composed almost entirely of water molecules frozen into tiny ice crystals. Picture W3IRS5, a star-forming region located 6,500 light-years away in the constellation Cassiopeia, where temperatures drop low enough for water to condense around dust grains. In 2011, astronomers using the Herschel Space Observatory detected water vapor streaming from protostars within this cloud at speeds exceeding 200,000 kilometers per hour, jets of steam blasting into space. The total amount of water in some molecular clouds exceeds all the water in Earth's oceans by factors of millions. Scientists believe these ice-coated grains may have delivered water to early Earth through cometary impacts. This reminds us that the universe manufactures the ingredients of life abundantly, scattering them throughout space with careless generosity. Certain stars pulsate with such regularity they serve as cosmic measuring sticks, allowing astronomers to calculate distances across the galaxy. Imagine Cepheid variables, stars that brighten and dim over periods ranging from days to months, their luminosity directly related to their pulsation period. Henrietta Swan Leavitt discovered this relationship in 1912 while studying stars in the Magellanic Clouds at the Harvard College Observatory, establishing a method that revolutionized astronomy. By measuring how bright a cepheid appears versus how bright it actually is, astronomers can determine its distance with remarkable precision. This technique was used by Edwin Hubble in 1929 to prove that galaxies exist beyond the Milky Way, fundamentally changing our understanding of the universe's scale. To think that the heartbeat of certain stars could unlock cosmic distances is a reminder that nature provides the tools we need to understand it. The Milky Way contains vast bubbles of hot gas blown outward by supernova explosions, creating cavities hundreds of light-years across. Consider the local bubble, a region of low-density gas surrounding our solar system, extending roughly 300 light-years in all directions. This cavity was excavated by approximately 15 supernova that exploded within the past 10 to 20 million years. According to research published in 2022 by astronomers at the Space Telescope Science Institute, the interior temperature exceeds 1 million degrees Celsius. Though the gas is so diffuse, it poses no danger to Earth. Our solar system entered this bubble about 5 million years ago and will remain within it for another 3 million years. In a sense, we live inside a cosmic wound, a scar left by stellar violence that predates human existence by eons. Some stars are born in such massive clusters that their combined gravity begins to shape the surrounding galaxy. Picture superstar clusters, regions where millions of stars form simultaneously, their collective radiation and stellar winds creating pressures that can halt further star formation. R136, located in the Tarantula Nebula, is one such cluster, containing more than 100,000 stars in a volume just 35 light-years across. Discovered in detail by the Hubble Space Telescope in 2010, this cluster includes some of the most massive stars known, several exceeding 150 solar masses. The intense ultraviolet radiation from these giants ionizes surrounding gas for hundreds of light-years, creating glowing shells visible across intergalactic distances. Scientists believe similar clusters were more common in the early universe, when galaxies were younger and gas was more abundant. This reminds us that star formation is not always a gentle process, but can be an act of cosmic violence. The Milky Way produces cosmic rays, high-energy particles that race through space at nearly the speed of light, their origins still debated. Imagine protons accelerated to energies millions of times greater than anything achieved in particle accelerators on Earth, striking atoms in the upper atmosphere and creating cascades of secondary particles. Supernova remnants, like Cassiopeia, A located 11,000 light-years away, are suspected sources, their expanding shockwaves acting as natural particle accelerators. Observations from NASA's Fermi Gamma Ray Space Telescope in 2013 detected gamma rays from these remnants, confirming they can accelerate particles to extreme velocities. However, the most energetic cosmic rays, those exceeding a billion electron volts, remain mysterious, possibly originating from supermassive black holes or exotic phenomena we have yet to identify. To think that invisible particles, born in distant explosions, constantly stream through our bodies is humbling. There are stars that have been caught in the act of being torn apart by black holes, their material stretched into glowing streams. Consider tidal disruption events, rare occurrences when a star wanders too close to a supermassive black hole and is ripped apart by gravitational forces. In 2019, astronomers using the All-Sky Automated Survey for Supernova detected ASASS N19BT, a star being consumed by a black hole 375 million light-years away. The event produced a brilliant flare visible for months as the star's gas spiraled into an accretion disk, heating to millions of degrees and emitting X-rays and ultraviolet light. NASA's TESS satellite captured the brightening in real time, providing unprecedented detail about how black holes feed. Scientists estimate these events occur roughly once every 10,000 years per galaxy. In a sense, black holes are not just cosmic drains, but cosmic spectacles, turning destruction into light. The Milky Way contains stars that have been flung so far from the galactic plane they now orbit above and below the disk like cosmic satellites. Picture stars moving through the halo at distances exceeding 100,000 light-years from the galactic center, their orbits taking them through regions almost devoid of other stars. In 2007, astronomers using the Sloan Digital Sky Survey discovered the Sagittarius Stream, a trail of stars torn from a dwarf galaxy that now arcs above and below our galaxy's disk. These halo stars travel on highly elliptical paths, plunging through the disk every few 100 million years before returning to the emptiness above. Chemical analysis reveals many originated in smaller galaxies that were absorbed long ago, making them immigrants rather than natives. To think that stars can spend most of their lives in the darkness between galaxies reminds us that the cosmos contains vast empty spaces between its islands of light. Some nebulae are shaped not by stellar winds, but by magnetic fields that twist and compress gas into intricate structures. Imagine the Helix Nebula, located 650 light-years away in the constellation Aquarius, where a dying star has ejected its outer layers in a pattern resembling a cosmic eye. Observations from the Hubble Space Telescope in 2003 revealed thousands of gaseous knots within the nebula, each one about twice the size of our solar system, formed where dense clumps of gas resist the expanding shell. The central white dwarf radiates ultraviolet light that ionizes the surrounding material, causing it to glow in shades of red, green, and blue. The nebula spans roughly 2.5 light-years across and will continue expanding, for tens of thousands of years before fading into darkness. In a sense, dying stars create their own monuments, sculpting their remains into forms that outlast them by millennia. There are regions of the Milky Way where stars are born inside pillars of gas that stretch for light years, shaped by radiation from nearby giants. Consider the Eagle Nebula, located 7,000 light-years away in the constellation Serpens, home to the famous pillars of creation photographed by the Hubble Space Telescope in 1995. These columns of molecular hydrogen and dust reach heights of approximately 4 to 5 light-years. Their tips eroded by intense ultraviolet radiation from massive stars formed earlier in the same region. Inside the pillars, gravity slowly compresses pockets of gas until they collapse into protostars, hidden from visible light but detectable in infrared. However, scientists estimate that a supernova explosion roughly 6,000 years ago may have already destroyed the pillars, though the light from that destruction will not reach Earth for another 1,000 years. This reminds us that we observe the galaxy not as it is, but as it was, seeing only echoes of events long concluded. The Milky Way rotates in a way that defies the laws of motion we observe on Earth, requiring the existence of something invisible to explain. Picture the galactic disk spinning like a record, but instead of slowing down toward the edges, stars maintain roughly the same velocity regardless of their distance from the center. Astronomer Vera Rubin discovered this anomaly in the 1970s while measuring rotation curves of spiral galaxies using spectrographic observations at the Kitt Peak National Observatory. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system move more slowly than inner ones. The fact that they do not suggests the galaxy contains far more mass than we can see, leading to the theory of dark matter. In a sense, the Milky Way is held together by something we cannot detect, a cosmic glue that reveals itself only through its gravitational effects. Some stars are caught in binary systems so extreme that one star is slowly vaporizing its companion through intense radiation. Imagine a pulsar spinning hundreds of times per second, its magnetic field channeling radiation into beams that blast a nearby companion star, heating its surface to tens of thousands of degrees. Black Widow pulsars, named for the spider that consumes its mate, were first identified in 1988 when astronomers detected PSRB 1957+20. Using the Arecibo Observatory in Puerto Rico, the pulsar's radiation heats its companion to such extremes that material boils off the surface, forming a cloud of ionized gas around the system. Eventually, the companion may be completely evaporated, leaving only the pulsar behind. Scientists have identified dozens of such systems across the Milky Way, each one a slow-motion execution spanning millions of years. This reminds us that even among stars, relationships can be fatal. The Milky Way produces gamma-ray bursts from colliding neutron stars, brief flashes that release more energy than the Sun will produce in its entire lifetime. Consider GW1 70817, detected on August 17, 2017. By the LIGO and Virgo gravitational wave observatories, the first neutron star merger observed through both gravitational waves and electromagnetic radiation. Located 130 million light-years away in the galaxy NGC 4993, the collision produced a kilonova explosion that synthesized vast quantities of gold, platinum, and other heavy elements, scattering them into space. Follow-up observations using telescopes worldwide captured the event's afterglow across multiple wavelengths, from gamma rays to radio waves. Scientists estimate that all the gold in the universe was created in such mergers, forged in conditions of unimaginable density and temperature. To think that the ring on someone's finger was born in the collision of dead stars billions of years ago is humbling. There are clouds in the Milky Way so vast they contain enough material to create millions of stars, yet remain cold and dark for millions of years. Picture the Taurus molecular cloud, located 430 light-years away, a sprawling structure covering more than 50 square degrees of sky, equivalent to 250 full moons. Despite containing roughly 30,000 solar masses of gas and dust, this cloud is forming stars at a remarkably slow rate, producing only a few new suns every million years. Observations from the Herschel Space Observatory in 2010 revealed that turbulence within the cloud prevents rapid collapse, maintaining a delicate balance between gravity and internal pressure. The cloud's low density and frigid temperature, hovering around -260 degrees Celsius, mean that star formation proceeds gradually rather than explosively. In a sense, not all cosmic nurseries are efficient. Some wait patiently for conditions to align before giving birth. Certain stars orbit the galactic center on paths so eccentric they spend most of their lives far from the Milky Way's disk before plunging through it at high speed. Imagine stars following orbits that take them 200,000 light-years from the galaxy, into regions where the density of stars is so low they might go millions of years without passing near another sun. High-velocity stars in the galactic halo were first studied systematically by astronomer Nancy Roman in the 1950s, who noticed their unusual motions and chemical compositions. These stars often have lower metallicity than disk stars, suggesting they formed in the early universe or in satellite galaxies later absorbed by the Milky Way. Measurements from the Gaia spacecraft have traced thousands of such orbits, revealing a complex history of galactic interactions. To think that some stars are perpetual wanderers, spending most of their existence in exile, reminds us that the galaxy is not a single community but many overlapping populations. The Milky Way contains stellar corpses called black holes that emit nothing but consume everything that approaches too closely. Picture stellar mass black holes, the collapsed cores of massive stars, scattered throughout the galaxy like cosmic sinkholes. Astronomers estimate the Milky Way contains roughly 100 million black holes, most of them invisible and detected only when they interact with nearby matter. In 2019, the Event Horizon Telescope collaboration produced the first image of a black hole's shadow, though it was located in the galaxy M87, not in the Milky Way. Closer to home, Cygnus X1, discovered in 1964 as one of the first black hole candidates, contains a black hole weighing approximately 21 solar masses, orbiting a blue supergiant star every 5.6 days. As gas from the companion star falls toward the black hole, it forms an accretion disk that heats to millions of degrees, emitting X-rays detectable from Earth. In a sense, black holes are not empty voids, but active consumers, revealing themselves through the light of their meals. Some stars are so massive they live fast and die young, burning through their fuel in just a few million years. Consider Eta Carinae, located 7,500 light-years away in the constellation, a binary system containing stars with a combined mass exceeding 120 times that of the Sun. In the 1840s, this system underwent a massive eruption called the Great Eruption, temporarily becoming the second brightest star in the night sky and ejecting material equivalent to several solar masses. Observations from the Hubble Space Telescope revealed that the ejected material formed a bipolar nebula called the homunculus, expanding at speeds exceeding 700 kilometers per second. Scientists predict Eta Carini will explode as a supernova within the next million years, possibly producing a gamma-ray burst if its core collapses into a rapidly spinning black hole. To think that we are witnessing a star in its final moments, a cosmic giant preparing for death, reminds us that all brilliance is temporary. The Milky Way's center hosts a cluster of massive stars orbiting so close to the supermassive black hole that their motions test the limits of relativity. Picture the S-star cluster, a group of stars packed within a light year of Sagittarius A*, moving at speeds that would cross the distance from Earth to the Moon in seconds. Star S2, monitored continuously since 1992 by astronomers at the European Southern Observatory, completed its most recent close approach in May 2018, passing within 17 light-years of the black hole at 7,650 kilometers per second. During this passage, measurements confirmed relativistic effects, including gravitational redshift, where the star's light was stretched to longer wavelengths by the intense gravity. The observations matched Einstein's predictions with remarkable precision, providing the strongest evidence yet that general relativity holds even in extreme environments. In a sense, these stars are natural laboratories, conducting experiments we could never perform on Earth. There are nebulae that shine with colors invisible to human eyes, their beauty revealed only through instruments sensitive to infrared and ultraviolet light. Imagine the Orion Nebula, located 1,344 light-years away, appearing as a small fuzzy patch to the naked eye but blazing with complexity when viewed through telescopes equipped with specialized filters. Observations from the Spitzer Space Telescope in 2006 penetrated the dust clouds surrounding newborn stars, revealing protostars still gathering mass from their surrounding disks. The nebula contains approximately 2,000 stars in various stages of formation, their intense radiation sculpting cavities in the surrounding gas. At its heart lies the trapezium cluster, for massive stars whose combined ultraviolet output ionizes the entire nebula, causing it to glow. To think that most of the universe's beauty exists beyond our perception reminds us that our senses capture only a fraction of reality. The Milky Way produces X-ray bursts from neutron stars that suddenly accrete material from companion stars, releasing energy in milliseconds. Consider X-ray pulsars, neutron stars with powerful magnetic fields that channel in falling gas onto their poles, creating hotspots that emit X-rays. Hercules X1, discovered in 1972 by the Uhuru satellite, is one such system, a neutron star pulling material from a blue giant companion every 1.7 days. The neutron star spins once every 1.24 seconds, causing its X-ray emission to pulse as the hotspots rotate in and out of view. During accretion bursts, the system brightens dramatically, releasing energy equivalent to 100,000 suns. Observations from the Chandra X-ray Observatory revealed complex interactions between the neutron star's magnetic field and the inflowing gas, creating shockwaves and turbulence. In a sense, neutron stars are cosmic recyclers, consuming the remains of their companions and transforming them into light. Some stars eject shells of gas in perfect spheres, their outer layers peeling away like cosmic onions. Picture the Cat's Eye Nebula, located 3,000 light-years away in the constellation Draco, where a dying star has expelled at least 11 distinct shells over thousands of years. Discovered in detail by the Hubble Space Telescope in 1994, this planetary nebula displays concentric rings, jets, and filaments, suggesting the central star underwent multiple episodes of mass loss. The shells are ionized by ultraviolet radiation from the hot white dwarf at the center, causing them to glow in characteristic colors determined by their chemical composition. Scientists believe the complex structure may result from interactions with an unseen companion star that orbits the white dwarf. To think that a star's death can create such intricate beauty reminds us that endings in the cosmos are transformations, not terminations. The Milky Way contains regions where magnetic fields are so strong they shape gas clouds into long filaments stretching across hundreds of light years. Consider the galactic center's radio filaments, first discovered in 1984 by Farhad Yousefzadeh using the Very Large Array in New Mexico. These structures, some measuring over 150 light-years in length but only a few light-years wide, are composed of ionized gas threaded through powerful magnetic fields. The filaments emit synchrotron radiation as charged particles spiral along field lines at relativistic speeds. More than 100 such filaments have been identified near Sagittarius A*, arranged roughly perpendicular to the galactic plane. Scientists believe they are created by interactions between the supermassive black holes, activity, and the surrounding interstellar medium. In a sense, the galaxy is wired with magnetic threads that channel energy across vast distances, a circulatory system invisible to our eyes. There are stars that have been observed to dim mysteriously and irregularly, their light blocked by something astronomers cannot fully explain. Imagine Tabby's star, officially designated KIC 8,462,852, located 1,470 light-years away in the constellation Cygnus, which dimmed by up to 22% over irregular intervals. Discovered in 2015 by astronomer Tabitha Boyajian using data from NASA's Kepler Space Telescope. This behavior puzzled scientists because no known planetary transit or stellar process could account for such dramatic, asymmetric dimming. Theories ranged from swarms of comets to disintegrating planets to dust clouds, though none fully explained the observations. Follow-up studies in 2018 suggested that dust particles of various sizes might be responsible, but the mystery remains partially unsolved. To think that a single star can challenge our understanding reminds us that the universe still holds phenomena we have not yet categorized. The Milky Way produces radio waves from hydrogen gas spread throughout the galactic disk, creating a constant hum detectable by radio telescopes. Picture the 21-centimeter line, electromagnetic radiation emitted when a hydrogen atom's electron flips its spin, a quantum transition that occurs spontaneously in the vast clouds between stars. This emission was predicted, theoretically, by Hendrik van der Hulst in 1944, and first detected in 1951 by Harold Ewan and Edward Purcell at Harvard University using a horn antenna mounted outside a laboratory window. The 21-centimeter line revolutionized astronomy by allowing scientists to map the Milky Way's structure even through dense dust clouds that block visible light. Observations revealed the galaxy's spiral arms, rotation speed, and the distribution of hydrogen throughout the disk. In a sense, the galaxy whispers its secrets in radio waves, speaking a language we learned to understand only recently. Some stars are so cool their surfaces are barely hotter than a summer day on Earth, glowing dully in infrared rather than visible light. Consider brown dwarfs, objects too massive to be planets but too small to sustain hydrogen fusion in their cores. WISEO 8550714. Discovered in 2014 by astronomer Kevin Luman using data from NASA's Wide Field Infrared Survey Explorer, holds the record as the coldest known brown dwarf, with a surface temperature around -23 degrees Celsius. located just 7.2 light-years from Earth. This object is roughly 5 times the mass of Jupiter and may have water clouds in its atmosphere. Brown dwarfs bridge the gap between planets and stars, numbering in the billions throughout the Milky Way, yet remaining mostly invisible due to their faint emissions. To think that objects colder than winter exist in the darkness between stars reminds us that the cosmos is not uniformly hot and bright, but contains vast regions of cold and shadow. The Milky Way's spiral arms are nurseries for massive star clusters that form all at once from collapsing giant molecular clouds. Picture NGC 3603, located 20,000 light-years away in the constellation Carina. A young cluster containing more than 10,000 stars packed into a region just 20 light-years across. Observations from the Hubble Space Telescope in 2007 revealed that the cluster is only 1 to 2 million years old, meaning all its stars formed in a brief cosmic instant. The most massive stars in the cluster exceed 100 solar masses and burn with such intensity they will exhaust their fuel and explode as supernova within just a few million years. The cluster's formation consumed an entire molecular cloud weighing tens of thousands of solar masses, converting it into stars with remarkable efficiency. In a sense, star formation can be a sudden, violent process, consuming vast reservoirs of gas in brief bursts of creation. There are stars that have been caught transitioning between life stages, their outer layers expanding and contracting as they struggle against gravity. Imagine Betelgeuse, a red supergiant located 548 light-years away in the constellation Orion, which dimmed dramatically in late 2019 and early 2020, dropping to about 40% of its usual brightness. Astronomers using the Very Large Telescope in Chile determined that the dimming was caused by a massive ejection of dust that temporarily blocked our view of the star's surface. Betelgeuse is in the late stages of its life, fusing heavier elements in its core while its outer layers pulsate irregularly, growing and shrinking over periods of months to years. The star is expected to explode as a supernova within the next 100,000 years, an event that will be visible from Earth in daylight. To think that we are watching a giant star's final breaths reminds us that even the most constant features of our sky are temporary. The Milky Way contains clouds of antimatter that annihilate with normal matter, producing gamma rays detectable from Earth. Consider the antimatter fountain near the galactic center, where electrons and their antimatter counterparts, positrons, collide and destroy each other, releasing gamma rays at a characteristic energy of 511 kiloelectron volts. This emission was first detected in the 1970s by balloon-borne gamma ray detectors and later mapped in detail by the Integral spacecraft launched by the European Space Agency in 2002. The source of these positrons remains debated, with candidates including radioactive decay from supernova, emissions from the central black hole, or even hypothetical dark matter particles. The antimatter cloud extends roughly 10,000 light-years above and below the galactic plane, glowing invisibly as matter and antimatter wage their eternal war. In a sense, the galaxy is a battleground where matter's mirror image exists, briefly before being consumed. Some nebulae contain molecules so complex they hint at the chemistry that leads to life. Picture the Horsehead Nebula, located 1,375 light-years away in the constellation Orion, where astronomers have detected more than 100 different molecules, including formaldehyde, methanol, and even amino acids. Observations using the IRAM radio telescope in 2001 revealed glycine, the simplest amino acid, within the star-forming region W3, suggesting that the building blocks of proteins can form naturally in space. These molecules assemble on the surfaces of dust grains, where ice mantles provide a substrate for chemical reactions driven by ultraviolet radiation and cosmic rays. When new stars form and heat their surroundings, these molecules evaporate into the gas phase, where they can be detected through their characteristic spectral signatures. To think that the chemistry of life may be universal, occurring wherever conditions permit, is both humbling and exciting. The Milky Way rotates at approximately 828,000 kilometers per hour at the Sun's location, carrying our entire solar system through space. Consider that while Earth orbits the Sun at 107,000 kilometers per hour, the Sun itself is racing around the galactic center at more than 7 times that speed. This motion is imperceptible in human lifetimes because the distances involved are so vast that the Sun takes 225 million years to complete one orbit. The solar system is also moving perpendicular to the galactic plane, oscillating above and below the disk like a wave with a period of approximately 64 million years. Some scientists have speculated this oscillation may correlate with mass extinction events on Earth, as passing through the denser galactic plane increases the likelihood of comet impacts, though this hypothesis remains controversial. In a sense, we are always in motion, passengers on a cosmic carousel we can never leave. There are stars that produce beams of particles so energetic they could be detected across intergalactic distances. Imagine blazars, supermassive black holes whose jets of relativistic particles point directly toward Earth, their emissions amplified by Doppler boosting. While most blazars lie in distant galaxies, the principles that govern them apply to smaller-scale phenomena in the Milky Way. Microquasars, like GRS 1915+105, discovered in 1992, consist of stellar mass, black holes accreting material from companion stars and ejecting jets at speeds approaching the speed of light. Observations from the Chandra X-ray Observatory revealed that these jets can extend for light years, creating shock waves as they slam into surrounding gas. The black hole in GRS 1915+105 weighs approximately 14 solar masses and rotates near the maximum rate allowed by general relativity. To think that small black holes can mimic the behavior of their supermassive cousins reminds us that physical laws scale across the cosmos. The Milky Way contains stellar streams that trace the orbits of destroyed galaxies, ghostly rivers of stars flowing through the halo. Picture the Monoceros Ring, a structure encircling the galactic disk, discovered in 2002 by astronomers analyzing data from the Sloan Digital Sky Survey. This ring consists of stars torn from the Canis Major Dwarf Galaxy as it was shredded by the Milky Way's tidal forces over hundreds of millions of years. The stream wraps around the galaxy multiple times, its stars spread along an orbital path that reveals the encounter's violence. Similar streams have been found throughout the halo, including the Orphan Stream and the Cetus Polar Stream, each one a fossil record of galactic cannibalism. To think that we can reconstruct the Milky Way's violent history by studying these stellar rivers reminds us that galaxies are not peaceful islands but predators. Some stars are born with companions so close they emerge from the womb already locked in orbit. Consider binary star systems like Alpha Centauri, our nearest stellar neighbor, located 4.37 light-years away, where two sun-like stars orbit each other every 79.91 years. Scientists estimate that more than half of all stars in the Milky Way are members of multiple systems, formed when collapsing gas clouds fragment into two or more cores. Observations from the Atacama Large Millimeter Array have captured proto-binary systems in the process of formation. Their accretion disks twisted into figure-8 shapes by mutual gravitational influence. Some binaries are so close their atmospheres merge, while others orbit at distances greater than Neptune's orbit around the Sun. In a sense, solitary stars like our Sun are unusual, cosmic loners in a galaxy where companionship is the norm. The Milky Way contains neutron stars that spin so fast they appear to vibrate, their surfaces rippling with oscillations that reveal their internal structure. Picture a star no larger than Manhattan Island, yet weighing more than the Sun, rotating 600 times per second while simultaneously vibrating at specific frequencies. In 1998, astronomers detected quasiperiodic oscillations from SGR 180620 using NASA's Rossi X-ray Timing Explorer, revealing that neutron star crusts can crack and reform like tectonic plates on Earth. These starquakes release enormous energy, sending seismic waves through the star's interior that cause the entire surface to ring like a struck bell. The frequencies of these oscillations allow scientists to probe conditions inside neutron stars where matter exists in states impossible to recreate in laboratories. To think that we can study the interior of objects 50,000 light-years away by listening to their vibrations reminds us that the universe reveals itself in unexpected ways. Some regions of the Milky Way glow with a diffuse light called the galactic background, photons that have been scattered countless times before reaching our eyes. Imagine standing in a forest where sunlight filters through leaves, bouncing from branch to trunk to ground until the source becomes impossible to identify. The integrated galactic light, first measured accurately by the Pioneer 10 spacecraft in 1983 as it traveled beyond the planets, represents the combined glow of billions of faint stars too distant to resolve individually. This background contributes significantly to the night sky's brightness, even in the darkest locations on Earth. Observations from the New Horizons spacecraft in 2021, now beyond Pluto's orbit, provided the most accurate measurement yet, revealing that the Milky Way's collective starlight creates a faint but measurable glow throughout the solar system. In a sense, we are never truly in darkness but always bathed in the ancient light of countless distant suns. The Milky Way produces bursts of radio waves so brief and powerful they were initially mistaken for interference from human technology. Consider fast radio bursts, millisecond-long pulses of radio emission whose origins remained mysterious for over a decade after their discovery. In 2020, astronomers using the CHIME telescope in Canada detected FRB 200,428, the first fast radio burst confirmed to originate within the Milky Way, specifically from the magnetar SGR 1935-2154 located 30,000 light-years away. The burst lasted less than 1 millisecond but released as much energy in radio waves as the Sun produces, across all wavelengths, in 3 days. This discovery confirmed that at least some fast radio bursts come from magnetars, though many detected from other galaxies remain unexplained. To think that objects in our own galaxy can produce signals once thought to require extragalactic origins reminds us how much power can be concentrated in fleeting moments. There are clouds in the Milky Way where molecules assemble into chains hundreds of atoms long, complex organic structures floating in the void. Picture cyanopollens, carbon chain molecules detected in the Taurus molecular cloud by radio astronomers in 1997, containing up to 13 atoms arranged in linear structures. These molecules form on the surfaces of dust grains where ultraviolet light triggers reactions that would never occur in Earth's atmosphere. The Gotham survey, conducted using the Green Bank telescope between 2018 and 2021, detected benzonitrile and other aromatic molecules in the cold core TMC1, suggesting that even ring-shaped organic compounds can form naturally in space. Some astrobiologists speculate that comets and asteroids carrying these molecules may have delivered prebiotic chemistry to early Earth. In a sense, the galaxy is a vast chemistry laboratory, conducting experiments in conditions we can barely simulate, producing molecules that blur the line between chemistry and biology. The Milky Way's disk is not flat but warped like the brim of a hat, twisted by gravitational interactions with satellite galaxies. Imagine viewing the galaxy edge-on and seeing the disk curve upward on one side and downward on the other, deviating from a perfect plane by thousands of light-years. In 2019, astronomers using data from the Gaia spacecraft and Apogee survey created the most detailed three-dimensional map of the warp, revealing that it precesses like a spinning top with a period of approximately 600 million years. The warp is most pronounced in the outer regions, beyond 50,000 light-years from the center, where the gravitational influence of the large and small Magellanic Clouds distorts the disk's shape. This discovery challenges the notion that spiral galaxies are simple, elegant structures and reveals them as dynamic, evolving systems constantly reshaped by their environment. To think that our galaxy is bent out of shape by its smaller companions reminds us that nothing in the cosmos exists in isolation. Some stars emit so much radiation they blow away their own outer layers, shedding mass in powerful stellar winds. Consider Wolf-Rayet stars, massive evolved stars that have lost their hydrogen envelopes entirely, exposing cores rich in helium, carbon, and oxygen. WR-124, located 15,000 light-years away in the constellation Sagitta, ejects material at speeds exceeding 6 million kilometers per hour, creating a nebula called M1267 that glows from the star's intense ultraviolet output. Observations from the Hubble Space Telescope in 1998 revealed clumps and filaments in the ejected material, suggesting the mass loss occurs in discrete episodes rather than smoothly. These stars lose the equivalent of Earth's mass every 1,000 years, transforming themselves completely over just a few 100,000 years. To think that stars can essentially commit suicide, tearing themselves apart through their own energy output, is a reminder that even the most powerful objects have limits. The Milky Way contains stellar nurseries where magnetic fields are so tangled they prevent gas clouds from collapsing into stars. Picture the Pipe Nebula, a dark cloud located 600 light-years away where magnetic pressure balances gravitational attraction, creating a standoff that has lasted for millions of years. Observations published in 2019 by astronomers using the Sophia Airborne Observatory revealed that magnetic fields in this cloud are strong enough to support the gas against collapse, explaining why star formation proceeds so slowly. The field lines twist and loop through the cloud in complex patterns, creating regions where gas can flow freely and others where it remains locked in place. Only when turbulence or shock waves from nearby supernova disrupt these fields can star formation begin. In a sense, magnetism is not just a force that shapes matter but one that can prevent creation itself, holding raw material in stasis for eons. There are binary systems in the Milky Way where one star has already died and begun consuming its living companion. Imagine Algol, the demon star, located 93 light-years away in the constellation Perseus, where a white dwarf orbits a larger blue star every 2.87 days. Centuries ago, the white dwarf was the more massive star, but after exhausting its fuel and swelling into a red giant, it transferred most of its mass to its companion through a process called Roche lobe overflow. Now the roles are reversed, and material from the currently larger star flows back toward the white dwarf through an accretion stream. This system has been studied since ancient times because it eclipses regularly, dimming noticeably when the dimmer component passes in front of the brighter one. To think that stars can exchange mass like currency, reshaping each other through gravitational intimacy, reminds us that stellar evolution is not always a solitary process. The Milky Way produces cosmic dust by destroying stars, grinding down their remnants into particles smaller than smoke. Consider supernova remnants like Cassiopeia A, where the explosion of a massive star 340 years ago created a rapidly expanding shell of debris. Observations from the Spitzer Space Telescope in 2008 detected large quantities of freshly formed dust within the remnant, including silicates, carbon, and iron compounds. Scientists estimate that a single supernova can produce enough dust to make thousands of Earth-sized planets, seeding the galaxy with the raw materials for future star and planet formation. This dust eventually spreads throughout the interstellar medium, mixing with gas clouds and being incorporated into the next generation of stellar systems. In a sense, we are made of stellar shrapnel, atoms forged in dying stars and scattered across the galaxy to eventually assemble into planets, oceans, and living things. Some pulsars emit beams so precisely timed they rival the best atomic clocks ever built. Picture PSR J04374715, located 510 light-years away in the constellation Pictor, which rotates 173.7 times per second with such regularity that its period changes by less than 1 part in a billion per year. Discovered in 1993 by astronomers using the Parkes Radio Telescope in Australia, this pulsar has been monitored continuously for decades, allowing scientists to detect tiny variations caused by gravitational waves passing through the galaxy. Networks of pulsars called pulsar timing arrays may eventually detect low-frequency gravitational waves from supermassive black hole mergers across the universe. The precision of these natural clocks allows astronomers to test fundamental physics, including searching for variations in gravitational constants over cosmic time. To think that nature has constructed timekeepers more stable than anything we have engineered reminds us that the universe operates with mechanical precision beneath its apparent chaos. The Milky Way's supermassive black hole occasionally flares with X-ray emission when asteroids or small clouds fall into it. Imagine Sagittarius, a asterisk consuming objects the size of comets, briefly heating their material to millions of degrees before they vanish forever beyond the event horizon. In 2013, astronomers worldwide watched as the gas cloud G2 approached the black hole, predicting a dramatic brightening that never materialized because the cloud proved more resilient than expected, possibly containing a star at its core. However, smaller flares occur regularly, detected by observatories like Chandra and XM Newton, suggesting that the black hole feeds on a steady diet of asteroids and planets torn from stars orbiting nearby. Each flare lasts minutes to hours, releasing energy equivalent to millions of nuclear bombs. To think that the galaxy's center consumes matter constantly, in small bites rather than great feasts, reminds us that cosmic violence often occurs on scales we can barely detect. There are regions in the Milky Way where gas clouds collide at speeds exceeding 100 kilometers per second, triggering bursts of star formation. Consider the W43 molecular complex, located 19,000 light-years away, where colliding clouds have created one of the most active star-forming regions in the galaxy. Observations from the Herschel Space Observatory in 2012 revealed that W43 produces stars at a rate comparable to entire dwarf galaxies, converting roughly 100,000 solar masses of gas into stars over just a few million years. The collision compresses the gas to densities high enough to overcome magnetic support and turbulent pressure, allowing gravity to win decisively. These cloud collisions may explain how massive star clusters form, concentrating stellar birth into brief, intense episodes. In a sense, creation in the cosmos often requires violence. The collision of vast structures moving at speeds no human vehicle could survive. The Milky Way contains brown dwarfs that wander alone through space, too small to shine but massive enough to generate faint heat. Picture these failed stars, objects between 13 and 80 Jupiter masses, glowing dimly in infrared as they slowly cool over billions of years. The Wide-Field Infrared Survey Explorer discovered thousands of brown dwarfs between 2010 and 2011, revealing that they may outnumber normal stars in some regions of the galaxy. WISE 1049 to 5319, located 6.5 light-years away, is a binary brown dwarf system where two objects orbit each other every 25 years. Neither one capable of sustaining hydrogen fusion. These objects blur the distinction between planets and stars, possessing characteristics of both yet belonging fully to neither category. To think that the galaxy is populated by countless objects that generate warmth but no light reminds us that the cosmos contains more than the bright beacons we typically observe. Some nebulae contain filaments of shocked gas moving at supersonic speeds, creating cosmic shockwaves visible across light years. Imagine the Cygnus Loop, a supernova remnant 2,600 light-years away spanning 3 degrees of sky, roughly 6 times the diameter of the full moon. The explosion that created this structure occurred approximately 20,000 years ago, and the expanding shell continues to plow through surrounding gas at speeds exceeding 400 kilometers per second. Where the shell collides with denser pockets of interstellar material, it creates bright filaments visible through small telescopes, including the famous Veil Nebula. Observations from the Hubble Space Telescope revealed intricate structures within these filaments, including regions where magnetic fields have been compressed and amplified. To think that we can observe the aftermath of an explosion that occurred when mammoths still walked Earth reminds us that cosmic events unfold on timescales both longer and shorter than human history. The Milky Way produces organic molecules in conditions so harsh they would destroy any life we know, yet these molecules persist and accumulate. Consider polycyclic aromatic hydrocarbons, ring-shaped carbon molecules detected throughout the galaxy through their characteristic infrared emissions. The Spitzer Space Telescope's surveys between 2003 and 2020 found these molecules in planetary nebulae, reflection nebulae, and even in the diffuse interstellar medium, suggesting they are among the most abundant organic compounds in space. These molecules can survive temperatures of thousands of degrees and intense ultraviolet radiation, protected by their stable ring structures. Some scientists believe they may have seeded Earth with organic material delivered by meteorites and comets during the planet's formation. In a sense, the building blocks of complex chemistry are everywhere in the galaxy, waiting for the right conditions to assemble into something more. There are stars in the Milky Way that have been ejected by three-body interactions, flung away when binary systems encounter a third star. Picture a close approach where gravitational forces become chaotic, angular momentum is exchanged violently, and one star is accelerated to escape velocity while the other to bind more tightly. Simulations by astronomers at Northwestern University in 2017 showed that up to 10% of binary stars may be disrupted this way in dense star clusters, scattering individual stars throughout the galaxy. Some of these ejected stars become hypervelocity objects, while others simply drift away at more modest speeds, forever separated from their birthplaces. The survivors of these encounters carry chemical signatures that reveal their origins in crowded environments. To think that stars can be exiled through random encounters reminds us that chaos and chance govern the cosmos as much as orderly physical laws. The Milky Way's spiral arms are marked by chains of massive young stars that live fast and die spectacularly. Imagine OB associations, loose groups of hot blue stars scattered across hundreds of light-years, burning through their fuel at prodigious rates. The Scorpio-Centaurus Association, the nearest OB association to Earth at approximately 400 light-years away, contains several hundred massive stars aged between 5 and 20 million years. Studies published in 2016 using data from the Gaia spacecraft revealed that stars in this association are expanding outward from common points of origin, suggesting they formed in several distinct bursts of star formation. These massive stars flood their surroundings with ultraviolet radiation, ionizing huge regions and triggering the formation of new stars in adjacent clouds. To think that certain stars are born in groups, yet drift apart over millions of years, reminds us that even stellar communities are temporary. Some neutron stars have been caught glitching, suddenly spinning faster as their crusts crack and readjust. Picture the Vela pulsar, located 1,000 light-years away in the constellation Vela, which undergoes sudden spin-up events every few years, where its rotation period decreases by a few microseconds in seconds. First observed in 1969, shortly after the pulsar's discovery, these glitches are thought to occur when the neutron star's solid crust lags behind its superfluid interior, building stress until the crust fractures and transfers angular momentum. Observations from the Parkes Radio Telescope have detected dozens of glitches from various pulsars, each one providing clues about the exotic states of matter that exist at densities exceeding atomic nuclei. To think that neutron stars have earthquakes powerful enough to affect their spin is a reminder that these objects remain dynamically active millions of years after formation. The Milky Way contains stellar populations of different ages layered like sediment, each generation recording conditions from when it formed. Consider the thick disk, a component of the galaxy containing older stars with higher velocities and lower metallicities than stars in the thin disk where our Sun resides. These stars, typically 10 to 12 billion years old, orbit the galactic center on paths tilted relative to the current galactic plane, suggesting they formed when the Milky Way had a different structure. Spectroscopic surveys like Apogee have measured the compositions of hundreds of thousands of stars, revealing distinct chemical signatures that trace the galaxy's assembly history. Some thick disk stars may have originated in dwarf galaxies that merged with the Milky Way long ago. In a sense, the galaxy is an archaeological site where different layers reveal different epochs, each population a fossil record of cosmic history. There are clouds in the Milky Way where temperatures drop so low that molecules freeze onto dust grains, coating them with icy mantles. Picture prostellar cores, the coldest and densest regions within molecular clouds, where temperatures hover around 10 degrees above absolute zero. The Taurus molecular cloud contains dozens of these cores, some weighing just a few solar masses, yet destined to collapse into new stars. Observations from the Herschel Space Observatory detected ice-coated grains within these cores, their surfaces covered with frozen water, carbon dioxide, methanol, and more complex organics. As cores collapse and heat increases, these ices sublimate, releasing molecules into the gas phase where they can participate in the chemistry surrounding newborn stars. To think that the materials that will someday form planets begin as frost on microscopic particles reminds us that even the largest structures grow from the smallest seeds. The Milky Way contains stars that rotate so slowly they take years to complete a single spin, their surfaces moving at walking speed. Imagine a red giant star swollen to enormous size, its outer layers so tenuous and distant from the core that rotational momentum has been stretched thin across a vast circumference. Betelgeuse, though primarily known for its size and variability, rotates approximately once every 36 years. According to measurements published in 2017 using interferometry from the Very Large Telescope, compare this to our Sun, which completes a rotation every 25 days, and the contrast becomes striking. As stars evolve off the main sequence and expand, conservation of angular momentum dictates they must spin more slowly, like an ice skater extending their arms. To think that stellar surfaces can move slower than a gentle breeze reminds us that size and speed are inversely related across cosmic scales. Some regions of the Milky Way contain molecular clouds so pristine they have never been contaminated by supernova ejecta. Picture pockets of primordial gas floating in the outer reaches of the galactic halo, their composition nearly identical to the hydrogen and helium mixture that filled the universe 13 billion years ago. In 2011, astronomers using the Keck Observatory in Hawaii detected metal poor clouds in the Leo Ring, a massive structure of neutral hydrogen gas orbiting the Milky Way at a distance of several 100,000 light-years. These clouds show metallicities less than 1/100th that of the Sun, suggesting they have remained isolated from the chemical enrichment that has transformed the galactic disk. If stars were to form in these clouds, they would represent a glimpse into stellar birth as it occurred in the early universe. In a sense, the galaxy preserves samples of its original material, cosmic archives that have escaped contamination for billions of years. The Milky Way produces molecules called buckyballs, soccer ball-shaped carbon structures in the hot atmospheres of dying stars. Imagine 60 carbon atoms arranged in a perfect sphere of pentagons and hexagons, a geometry so elegant it won its discoverers the Nobel Prize in Chemistry in 1996. In 2010, NASA's Spitzer Space Telescope detected Buckminster Furon, or C60, in the planetary nebula TC1, marking the first confirmed detection of these molecules in space. The discovery surprised scientists because buckyballs are remarkably stable despite their complexity, surviving temperatures exceeding 1,000 degrees Celsius in the harsh environment around dying stars. Subsequent observations found them in numerous planetary nebulae and even in reflection nebulae illuminated by young stars. To think that nature constructs geometric perfection from chaos, assembling precise molecular architecture without blueprint or intention, reminds us that elegance emerges spontaneously from physical law. There are stars in the Milky Way that have been magnetically arrested, unable to accrete matter from surrounding disks because of intense magnetic fields. Picture a young star in the process of formation, surrounded by a disk of gas and dust that should be falling inward to feed the growing protostar. Instead, powerful magnetic fields threading through the disk create a barrier that diverts the flow, channeling material into jets that shoot perpendicular to the disk at hundreds of kilometers per second. Observations from the Atacama Large Millimeter Array in 2018 revealed these magnetized structures in the protostar HH-212, located 1,300 light-years away in the constellation Orion. The magnetic field is so strong it prevents matter from reaching the star's surface directly, forcing it to spiral along field lines until it impacts near the poles. In a sense, stars are born fighting against the very forces that create them, their magnetic fields both guiding and resisting their growth. The Milky Way contains shells of neutral hydrogen gas blown outward by stellar winds, creating bubbles hundreds of light years across. Consider the local bubble, the cavity of hot low-density gas surrounding our solar system, carved out by approximately 15 to 20 supernovae that exploded over the past 10 to 20 million years. Research published in 2022 by astronomers at the Space Telescope Science Institute mapped the bubble's three-dimensional structure using data from Gaia, revealing that its walls are lined with dense molecular clouds where current star formation is concentrated. The Orion, Taurus, and Perseus molecular clouds all lie on the bubble's surface, suggesting that the ancient supernova may have triggered the formation of stars that now populate our local neighborhood. We currently reside within this cavity, traveling through gas 100 times less dense than the average interstellar medium. To think that we live inside a cosmic wound sculpted by stellar death reminds us that destruction creates the conditions for renewal. Some stars emit neutrinos in such quantities they could be detected across the galaxy if we had sensitive enough instruments. Imagine the core of a massive star in its final moments before supernova, where nuclear fusion has ceased and gravitational collapse begins, compressing matter to densities that force protons and electrons to merge into neutrons. This process releases a flood of electron neutrinos that carry away 99% of the supernova's energy, streaming outward at the speed of light through the collapsing star. Supernova 1987A, though located in the Large Magellanic Cloud rather than the Milky Way proper, provided humanity's first detection of supernova neutrinos when 25 particles were caught by detectors in Japan and the United States on February 23, 1987. Those 25 neutrinos, arriving hours before the light from the explosion became visible, confirmed theoretical predictions about stellar collapse. To think that invisible particles carry the majority of energy from the universe's most violent explosions reminds us that what we see is often the smallest part of what occurs. The Milky Way rotates differentially, meaning stars at different radii orbit at different speeds, creating shear that stretches structures over time. Picture two gas clouds initially side by side, gradually separated as one completes its orbit faster than the other, their separation increasing over millions of years. This differential rotation is why spiral arms appear to wind up, though the density wave theory explains how the pattern persists despite individual stars and clouds moving through it. Measurements from the Gaia spacecraft published in 2018 created velocity maps showing that the inner galaxy rotates faster than the outer regions, with rotational velocity decreasing beyond the Sun's orbit. This velocity gradient has profound effects on the evolution of molecular clouds and star clusters, stretching them into elongated structures aligned with the galactic rotation. In a sense, the galaxy is constantly stirring itself, mixing its contents through motion that varies with distance from the center. There are planetary nebulae in the Milky Way with jets that presses like wobbling tops, creating intricate spirals and helices. Imagine LL Pegasi, also known as IRAs 23,166 plus 1,655, located 3,000 light-years away, where a binary star system ejects material that forms a perfect spiral pattern. Hubble Space Telescope images captured in 2010 revealed a structure resembling a nautilus shell, created as material is ejected in a jet that rotates with the orbital period of the binary system, approximately 800 years. Each loop of the spiral represents one orbital period, allowing astronomers to trace the system's history backward in time. The precision of the pattern suggests remarkable stability in the mass loss process over thousands of years. To think that dying stars can create geometric art through the simple combination of ejection and rotation reminds us that complexity often arises from simple rules applied consistently. The Milky Way produces cosmic rays that bounce through the galaxy for millions of years before escaping or being absorbed. Picture a high-energy proton accelerated in a supernova remnant's shockwave, racing outward at nearly the speed of light, only to encounter magnetic field lines that deflect its path. The particle spirals along these field lines, bouncing back and forth between regions of stronger and weaker magnetic field in a process called magnetic mirroring. Over millions of years, a single cosmic ray might traverse the entire galaxy multiple times, gradually losing energy through interactions with gas, dust, and photons. Observations from the Pier Auger Observatory detected cosmic rays with energies exceeding electron volts, particles carrying as much energy as a well-thrown baseball compressed into a single atomic nucleus. To think that individual particles can carry such energy reminds us that the universe operates on scales both impossibly large and impossibly small. Some stars in the Milky Way are so metal-rich they challenge our understanding of chemical enrichment. Consider stars in the galactic bulge, the central region where stellar densities are highest and multiple generations of star formation have occurred. Observations from the Apache Point Observatory Galactic Evolution experiment found stars with iron abundances exceeding that of the Sun by factors of 2 or 3, suggesting they formed from gas already enriched by numerous supernovae. These metal-rich stars tend to be younger, found in regions where star formation has been ongoing for billions of years, allowing successive generations to incorporate the ashes of their predecessors. The gradient in metallicity from the outer halo to the inner bulge traces the galaxy's chemical evolution, a record of how elements have been redistributed over cosmic time. In a sense, stars carry their genealogy in their spectra, their compositions revealing where and when they formed. The Milky Way contains infrared dark clouds, regions so dense and cold they absorb even infrared radiation, appearing as silhouettes against background emission. Picture the Snake Nebula, a sinuous dark cloud stretching across 100 light-years in the constellation Ophiuchus. Identified in 2006 using data from the Spitzer Space Telescope, these clouds are invisible at most wavelengths, but can be mapped by the light they block or by their emission at millimeter wavelengths. Observations reveal they are among the densest structures in the interstellar medium, with central densities exceeding 1 million particles per cubic centimeter, roughly 100,000 times denser than typical interstellar space. Despite their density, they remain so cold that thermal pressure cannot prevent their gravitational collapse, making them prime sites for future star formation. To think that the galaxy contains regions darker than the space around them reminds us that darkness has depth and structure. There are Wolf-Rayet stars in the Milky Way surrounded by nebulae shaped like pinwheels, created by binary companions. Imagine WR104, located 8,000 light-years away in the constellation Sagittarius, where a Wolf-Rayet star and an Ob-type companion orbit each other every 242 days. As the Wolf-Rayet star ejects material in a powerful stellar wind and the companion orbits, the interaction creates a spiral pattern visible through infrared telescopes. Observations from the Keck Observatory revealed that the spiral rotates with the binary period, creating a cosmic Catherine wheel of dust and gas. Some scientists have speculated that WR104's rotation axis might be aligned toward Earth, meaning if it explodes as a supernova, its gamma-ray burst could potentially affect our planet, though this remains highly uncertain and controversial. To think that stellar death can create beauty even as it poses potential danger reminds us that the cosmos is simultaneously threatening and magnificent. The Milky Way's dark matter halo extends far beyond the visible disk, creating a gravitational cocoon that shapes the galaxy's dynamics. Consider that the luminous matter we observe, stars and gas combined, accounts for only about 15% of the galaxy's total mass. The remaining 85% consists of dark matter distributed in a roughly spherical halo extending perhaps 600,000 light-years from the galactic center, far beyond the visible spiral arms. Measurements of satellite galaxies' orbital velocities and the motion of stars in the outer disk allow astronomers to map this invisible component. Simulations published in 2020 by the illustrious TNG project showed that dark matter halos like the Milky Way's contain complex substructure, including streams and clumps left over from smaller halos that merged over billions of years. In a sense, the galaxy we see is merely the visible peak of a much larger invisible mountain. Some stars produce molecules called fullerenes that have been proposed as candidates for explaining diffuse interstellar bands. Picture mysterious absorption features in starlight that have puzzled astronomers since their discovery. In 1922, by Mary Lee Heeger at Lick Observatory, more than 500 diffuse interstellar bands have been catalogued, appearing in the spectra of stars across the galaxy, but their chemical origins remained unknown for decades. In 2015, astronomers using the Apache Point Observatory telescope tentatively identified two bands as matching the spectrum of ionized Buckminster Floron C60+, though this identification remains debated. If confirmed, it would solve one of the longest-standing mysteries in spectroscopy and demonstrate that complex carbon molecules are abundant throughout the interstellar medium. To think that molecules floating between stars can leave fingerprints in light that crosses the galaxy reminds us that space is not empty but filled with chemistry. The Milky Way contains echoes of ancient supernova explosions preserved in radioactive isotopes found in deep-sea sediments on Earth. Imagine iron-60, a radioactive isotope with a half-life of 2.6 million years, created only in supernova explosions and now detected in ocean floor samples. Research published in 2016 by scientists at the Technical University of Munich found elevated levels of iron-60 in sediment, layers dated to approximately 2 to 3 million years ago, and again at 6 to 7 million years ago. These isotopes must have been deposited by nearby supernova whose expanding shells of debris eventually reached Earth, showering the planet with cosmic fallout. The discoveries suggest that several supernova exploded within a few hundred light-years during the past 10 million years, possibly within the moving group that created the local bubble. To think that we can find evidence of stellar explosions in mud extracted from the ocean floor reminds us that Earth participates in galactic history. There are pulsars in the Milky Way that emit giant radio pulses thousands of times brighter than their average emission. Picture the Crab pulsar, the rapidly spinning neutron star at the heart of the Crab Nebula, which occasionally produces pulses visible even to small radio telescopes. First detected systematically in 2003 by astronomers using the Arecibo Observatory, these giant pulses arrive unpredictably, separated by seconds to hours of normal pulsations. The mechanism behind them remains debated, with theories ranging from magnetic reconnection events in the pulsar's magnetosphere to coherent emission from electron-positron plasma. Some giant pulse emitters, like PSRB 1937+21, produce bursts that, if scaled up, would rival the luminosity of fast radio bursts from other galaxies. To think that neutron stars can suddenly brighten by factors of thousands for microseconds reminds us that even objects we consider well understood can surprise us. The Milky Way produces molecules with handedness, asymmetric structures that exist in left and right-handed forms. Consider propylene oxide, a chiral molecule detected in 2016 by astronomers using the Green Bank telescope in a star-forming region called Sagittarius B2. This was the first definitive detection of a chiral molecule in interstellar space. Important because biological molecules on Earth overwhelmingly favor one-handedness over the other, left-handed amino acids and right-handed sugars. The observation raised questions about whether interstellar chemistry could have influenced biology's preference for specific chirality. Laboratory experiments suggest that circularly polarized ultraviolet light from young stars might preferentially destroy one form of chiral molecules, creating an imbalance that could seed planets with a predisposition toward specific handedness. In a sense, the galaxy may influence not just the quantity but the quality of chemistry available for life. Some stars in the Milky Way have been caught consuming planets, their atmospheres enriched with elements that should have settled into their cores long ago. Imagine a sun-like star that formed with a planetary system, then gravitationally perturbed one of its planets, sending it spiraling inward until it was engulfed and vaporized in the stellar atmosphere. In 2019, astronomers identified evidence for such consumption in the binary star system HD 240430, where one star showed higher abundances of refractory elements like iron and titanium compared to its companion. Since both stars formed from the same molecular cloud, their compositions should be identical unless one star accreted additional material. The excess elements match those expected from rocky planet consumption, suggesting the star swallowed one or more Earth mass bodies. To think that stars occasionally devour their children reminds us that planetary systems are not always stable havens but can be sites of violent reorganization. The Milky Way contains stellar fossils called subdwarfs, ancient stars with unusual compositions that reveal conditions in the early galaxy. Picture stars formed when the universe was less than 1 billion years old, containing almost no elements heavier than helium because few supernova had yet enriched the primordial gas. SD SSJ 102915 tambah 172.838. Discovered in 2011 by astronomers using the European Southern Observatory's Very Large Telescope, holds the record for the lowest metallicity ever measured in a star, with iron abundance roughly 1/millionth that of the Sun. This star is located 4,000 light-years away in the constellation Leo and has survived for approximately 13 billion years, making it one of the oldest objects in the galaxy. Its composition provides a direct window into the chemical state of the universe shortly after the first stars formed. To think that we can analyze starlight from objects nearly as old as time itself reminds us that astronomy is a form of time travel. Some molecular clouds in the Milky Way are threaded with filaments that channel gas toward dense cores where stars will form. Imagine the Herschel Space Observatory's surveys between 2009 and 2013 revealing a cosmic web of elongated structures, some stretching for dozens of light-years, yet measuring less than a light-year across. The integral-shaped filament in the Orion, a molecular cloud, observed in detail in 2014, shows gas flowing along its length towards several dense nodes where protostars are forming. These filaments appear to be nearly universal features of molecular clouds, suggesting that the galaxy organizes gas through large-scale processes before star formation begins. Their widths are remarkably consistent, typically around 0.1 light-years, possibly set by the balance between gravity and turbulent pressure. In a sense, the galaxy possesses a circulatory system of filaments that concentrates matter, guiding raw material toward sites of creation. The Milky Way produces X-ray binaries where neutron stars accrete matter so rapidly they shine with luminosities exceeding 100,000 suns. Consider ultraluminous X-ray sources, systems where compact objects draw gas from companion stars at rates far exceeding theoretical limits.